All right. So I did cancel class on Tuesday. My purpose for doing so is just it's cold, and I am sure all of you could think of something better to do than to watch 2.5 hours worth of lecture on YouTube, which sounds like a nightmare to me. I much prefer this in person. I don't know why, but I'm okay with doing 2.5 hours worth of lecture in person. Oh well. All right. How comfortable are you with resistance at this point? That is the kind of mentality I like. Yes. It's a very firm head shake. Okay, if I throw up a circuit like this, how comfortable are you that you could calculate the amount of power coming out of the voltage source? Mostly. Kind of. Getting some hesitance, but I'm getting some positivity here, okay? At this point, this is now in the past, okay? We're moving forward with more difficult content. And it's not because we aren't going to be hanging out with resistors anymore. It's because at this point, resistance is futile. We're going into capacitance. So, I remember the second time I taught this class, one of the students showed me this, which is a meme that's resistance is futile. Because you're jumping both ends. So, I mean, both ends start and end at the same node. So, yeah, funny joke. Well, we're moving on from resistance today to capacitance. Your reading assignment that's due tonight, I believe, covers both capacitance and inductance. Nope, that was due on Tuesday. You should all have had it done by now. We're not going to get to inductance yet. That is a little bit, that's where we should have been at this point, but we're not there yet. So we'll play a little bit of catch up trying to get back there. All right, does anybody know what capacitance is? Anybody have a guess? It's like electrical storage, yes. Okay. One of the interesting things about every physical system is that every physical system, because of the way calculus is set up, every physical system has a correlation to other physical systems. Okay? Electrical systems are modeled one way. Turns out you can model an electrical system like a hydraulic system, and the math is actually the same. You can model an electrical system like a rotational system, an axle with gears and spinning components. You can model them. The math is identical. So as we're covering math for electrical systems, I can bring in an analogy. Jacob said, a capacitor is like electric storage. Well, if you're going to use the hydraulic analogy, which is where the math is same as a hydraulic system, capacitance is like a water tank. Okay, and the idea here is you have a big water storage tank. This has an inlet pipe and it has an outlet pipe. Okay? And the difference in pressures between the inlet and the outlet It will define whether or not water is going into the tank or coming out of the tank. More water is going into the tank, more water is coming out of the tank. Okay? You will have times where the tank is filling up and where the water is rising because not as much water is coming out as is going in. Okay? You will have other times where the water level is falling because you have more coming out than is going in. And that's basically what a capacitor is. Okay? A capacitor is, it's like electron storage, as Jacob put it. But the definition of capacitance is a little bit more in-depth. Anytime you get a bunch of electrons together, hanging out, just blowing around, like electrons do, a bunch of electrons together do one thing. They create a giant electric field. Turns out it actually doesn't take very many electrons to create a giant electric field. Static electricity, you get a few electrons that transfer between you and like your cat, and it charges your whole body, to which all of a sudden you are electro, and like pew, pew, pew. And that's only a few electrons. Electron storage itself, in the presence of just electrons blowing around, electron storage creates a very large electric field. Okay? And what ends up happening here is when you have any amount of electrons all coagulating together, it turns into a giant electric field, and that is a source of energy. Okay? So what capacitance is it is a, in a physical sense, it is a set of plates separated by a dielectric that stores excess electrons and holes. Okay, now both of those are an important point to make. So let's break down the definition of what a capacitor is, and then I have one more point down here of what capacitance is, but I'll get back to it. So just breaking down the physical structure of a capacitor, you have two metal plates, or two conducting plates, and in between these two plates, there is a very strong electric field. Okay. Why is there an electric field? Because on one side, on one set of plates, you have what are known as holes. Okay? It's not an excess of protons. Having an excess of protons would give it a positive charge. However, having a deficiency in electrons does the same thing. We refer to this as holes in physics, because what you have is you have a material that is supposed to have X number of electrons in the matrix, and some of those electrons leave, leaving electron holes. They aren't real physical holes. They're just they're energy locations where electrons should be and are not. That is the definition of a hole. Okay. So on this end you have holes, and on this end you have an excess concentration of electrons. So you have too many electrons, too few electrons, and what that creates in between these two is a very large electric field. Okay? Most materials cannot handle a very large electric field between both ends. The whole reason why you can see electric charge jump in air is because air itself, while it is a very good dielectric, cannot handle a very large electron difference between the two ends of a wire, and it will cause a spark to happen. Okay? Lightning is what happens when air, as a dielectric, breaks down. You have an excess of charges located in the atmosphere, you have an excess of holes located on the ground, and the air, it forms a dielectric that breaks down, and you get lightning as a result. Okay? That's what electron shock is. It is a dielectric where there is a very strong electric field. Now in a perfect dielectric, electrons cannot jump between one terminal and another. It turns out there's something called electron tunneling where electrons can travel through just about any material. It does happen, so there is a trace amount of electric current that happens with electrons traveling from this end to this end. That's known as a parasitic effect, but that was in the reading. I wasn't planning on getting into that today. But in theory, and in a perfect capacitor, no charges go across the dielectric. In the best capacitor, no charges go across the dielectric. The dielectric is a no zone for electrons. Is the most insulating material you want. You don't want those plates transferring electrons. In fact, in some capacitors, if you do have electrons, a significant amount of electrons traveling through the dielectric, it will either cause it to start on fire or it will completely destroy the capacitance of the plates. It'll basically just turn it into a resistor. Okay? So, physical structure of a capacitor. Now, the last note on what capacitance is in the definition, capacitance, okay, in resistance, what happens with resistance is we calculated all the power that was going into resistors. Where does that power go? Does it just accumulate in the resistor like, oh boy, high score, woo, resistance power? Where does all that energy go? Heat. There are some resistors that, I mean, technically these are resistors too. So you can have electromagnetic radiation, but I mean, ultimately that even turns into heat. You are very right. Resistors change energy that comes out of the battery. All the power coming out of the battery, resistors change it into heat, or electromagnetic radiation, which eventually becomes heat, or mechanical movement, which eventually becomes heat. It turns into heat eventually. What a capacitor does is it converts power coming in into electric field energy. So when we're calculating the power that is being consumed by a capacitor, we are calculating the amount of energy change that is occurring at the capacitor between the two plates due to a change in the electric field at that location. All right? That's how we're going to define capacitance, because ultimately when we're looking at other components, it turns out inductors also have a little bit of capacitance because there's a small electric field there. It's not huge, but it does exist. And when you talk about parasitic effects, we model it as having a capacitor for that reason. Anytime you have an electric field, you have a capacitance. Anytime you have an electric field, you have a capacitance. Okay? It may be very small, maybe a very minute amount of capacitance, but anytime you have an electric field, you have a capacitance. Okay? And usually it's air that forms the dielectric there. Any questions on what a capacitor actually is? I'm doing my best to beat this to death because at this point, things are about to get weird. Warned you already that this is the point in the class where things start getting fun. I'm going to use the word fun very liberally here. Oh, dang, I did that on camera. Oh, drat. Terrible way to start my day off. I just danced on YouTube. Okay, very simple system. This is a capacitor. Some capacitors are shown like this. What this is a one-directional capacitor. What this means is that this one can store negative charges, this one can store holes, but not the other way around. If you were to put this in reverse, this would not be able to carry negative charges. It would transfer electrons across the dielectric, and you would have a current traveling through your capacitor, which would cause the dielectric to break down and just generally damage your capacitor. So this is a one-directional capacitor, only works in one way. Okay? And in these components, usually it'll show you a positive and a negative end. The positive end is the one that collects the electrons. The negative end is the one that collects the holes. It's exactly backwards from what's actually happening physically. Okay? In this system, I throw plus 5 volts across that capacitor. All right? There's 5 volts between node 1 and node 2. How do I know that? Because if I do Kirchhoff's voltage law, well, it's plus 5 volts minus 5 volts. So that means there's 5 volts across this. Kirchhoff's voltage law still applies here. Kirchhoff's current law still applies here. However, I guess I'm going to introduce the concept of the relationship between voltage and current in this system. And this is where things start to get weird. This capacitor currently has 5 volts across it. Okay? We know that because KVL has to be true. The relationship between voltage and current in a capacitor is given by V equals C di dt. Voltage is equal to the capacitance multiplied by the derivative of the current. Okay? So, question. What is my voltage on the capacitor in this circuit? It's 5. Does it change? If it does not change, the way that I have this circuit set up, that means dV dt equals 0, right? Right? Okay, no change in voltage, dV dt equals 0. That doesn't actually mean anything to us. But here is a no, I got this exactly backward. Yeah, dang it. I wrote this backwards. I equals C dV dt. Duh. My apologies. That's what I get for trying to memorize the formulas. Okay? So, I don't have any change in voltage here. Because I don't have any change in voltage, this value is 0. I have voltages throughout my system, but I do not have any current flowing. That is completely different than what we had for a resistor. In a resistor, when I had current flowing, that was the only time I could have any kind of voltage across the resistor. And the reason for that being, Ohm's law has to be true. V equals IR. For a resistor, there has to be a current in order for there to be a voltage. If the current is 0, the voltage is 0. In this system, current can be 0 and voltage can be non-zero. Similarly, in this system, voltage can be 0 and current can be non-zero. However, it's just instantaneous. It is very possible for that to happen. In a resistor, you cannot have a voltage if the current is 0. So we are now looking at a fundamental shift in the math involved in calculating these circuits. Dang you derivatives. You're driving me crazy. That was funnier in my head. Okay, so when I put up a simple circuit like this, this technically, if you're looking at the voltage in the capacitor, VC, okay? Let's say we're going to start at VC equals 0, and at time t equals 2 seconds, we're going to flip the switch, okay? So I'm going to say t equals 2, the switch is flipped. So if we're going to just plot the voltage across the capacitor for this system, this goes from starting at 0 volts. I do have other colors. I'm going to draw in blue. Oh man, I suck at drawing straight lines. Confession to make, I never graduated line school. I know, my parents were ashamed of me too. We're going to start out at 0, okay? At t equals 2. What happens to the voltage? Does it slowly climb up? Does it immediately spike up? What happens to it? Anybody want to guess? Any bold individual caring to go into uncharted territory? It's Tom Holland. Huh? It spikes up. Why does it spike up?
Because of 5 volts and it's getting resistant.
Because KVL still has to be true. In this circuit, if we were to go around this loop, right now, there is a 5 volt difference there. Okay? And your open circuit, which, by the way, you have a 5 volt difference, there's going to be a small amount of electric field generated at that open circuit, which is weird because that's almost like a capacitor. It's just kind of like an unregulated capacitor because we have no idea how many charges are there. It's storing charges. But there's 5 volts across those terminals, and then and then as soon as we close it, there are 0 volts across that terminal. So all 5 of the volts has to be across a capacitor. In this, we see an immediate spike that jumps up to Vs. Okay? Now that's not realistic. I'll tell you that right now. This is for a perfect capacitor. Real capacitors have some small amount of resistance in it. Because of the small amount of resistance, a real capacitor, the actual curve, I'll draw it in red. The actual curve ends up being an exponential function that looks more like this. Okay, that's a little exaggerated. it charges, most capacitors charge in a microsecond because they're so small. So yes, this is like 5 microseconds of time, but it charges up and it does have some curve. It's not just a straight line. There is a finite amount of time that it takes to charge that capacitor. In this circuit though, we're dealing with what is assumed to be an ideal capacitor. Therefore, we're going to assume it follows the blue line, okay? When we're following the red line, that actually gets into first order and second order systems, which we will get into either next week or the following week. And that's where things really get fun. Okay. I gotta go grab my book because there's a formula in there I need and I don't have it memorized. Okay. Very quickly, the definition of current. Depending on which class you're in, could be now, could be the present, or in this class, it's the rate change of flow of charges. I equals dq dt. Meaning, dq dt, here q is the number of charges, okay? I is the number of charges that travel per amount of time, dq dt. Okay, so that's what Q is. Q represents an electric charge. It's actually physically representing the motion of an electron. So, motion of electrons, that's what current is. Now here, for a capacitor, I equals C dV dt. Well, as you can see, I equals dq dt by definition of current, the amount of charges traveling per time. I also is equal to dV dt times capacitance C. We can just set these equal to each other, and it turns out Q is equal to C V. And I don't know why I didn't have that memorized. Once again, I thought that was funnier in my head. In my mind, I'm the greatest comedian. Last year, I made a joke in this class. It was so funny. I was trying not to laugh because, you know, laughing at your own jokes is like a sign that you're the worst comedian ever. So I was sitting there not laughing at my jokes, crying because I thought it was so funny. So yeah, I laugh at my jokes so I don't cry in front of you. You're welcome. I know it makes me a terrible comedian, but whatever. I saw an interview with Rowan Atkinson. That man has the greatest deadpan humor. I love him. He's the guy who plays Mr. Bean. Very British humor, very British style of humor. He's very intelligent, but every character he plays is kind of the haphazard dork. Man, I love Rowan Atkinson, though. Someday I wish I could drop funny humor just like him. That has nothing to do with class today. So, here's what we have. We have this relationship that is true for capacitors. Okay? Now, the power equation, when it comes to capacitors, if you remember power, What is the definition of power? Anybody remember? I gave all of these formulas second day of class. Voltage times current. P equals VI, or PIV. People like calling it PIV. In fact, I'm actually going to write it that way because that's how people remember it. It's PIV. Okay? Power equals current times voltage. If we were to write out the equation for that, for a capacitor, power is equal to the relationship between current and voltage is C dV dt. So power is equal to C dV dt times V. Look at that horribly ugly relationship. Or you can go with the alternative, is if you rearrange this, V is equal to 1 over C integral of I dt. Thanks, Sal. You're a real stand-up guy. How did you deadpan that? Teach me your knowledge.
What knowledge?
I hate it when I have students in class that are better comedians than me. I'm supposed to be the funny guy in here. This is the start of my stand-up career. Okay, so we could take this relationship, and then the other relationship that we can derive then using this equation is P equals I times, well, it's 1 over C times I times the integral of I dt. That's not a pretty relationship either. Neither of these power equations are good. These both suck. So, yeah. There's a reason why there was no power formula given to you in your book. It's because this is true. Don't even write it down. It's not worth your time. But I derived them for you, and they're true. On the other side of it, the energy equation is the integral, where energy is equal to the integral of power with time. If we took those power equations and we integrate them, we actually get a very nice formula. And that formula is another one that I don't have memorized. I wrote energy as E. Oftentimes it's represented as W. I think your textbook represents it as a W. What we can do is we can go ahead and write the energy on a capacitor with time is equal to 1/2 C V squared, where your voltage is also a function of time. 1/2 C V squared. Okay? And that is a nice formula. Nice. Now, because we have this relationship, we can also write that WT energy is equal to 1/2 C times V times Q. That's also valid. And just replace one of your V's with C and a Q. Wait, it's 1 over C, isn't it? No, never mind, sorry. There's no C here. It's just 1/2 V times Q. And then on the other side, you can take it and write the third equation, which is with no V's, 1 over 2 times Q squared divided by C. All three of those are valid equations. They're all the same equation. It's just derivations of this that use this. Just keep plugging that in over and over again, and you get 3 different equations. Nice. So that is our definition of capacitance. And those are all the equations that we have. This is the one you will need to know the most. Write this down, circle it, star it. I equals C dV dt is the most important one. Okay, second most important one that you should know is the WT equals 1/2 CV squared, which is your energy equation. Those are the 2 most important equations for a capacitor. Everything else we can just derive from that. Okay, you can take the derivative of this equation and find power. Okay? All right. Let's take a 10-minute break. We'll come back here at